Hi, yes, you can see me. It's dumpster diving time again. I found this down in the dumpster room. It's a 50-inch Ultra HD 4K Hitachi smart TV. Complete with stand, didn't have the remote control, couldn't find it. Pro dumpster diving tip. If you find stuff like this, try and find the remote control as well. They'll often throw it like in the dumpster. This wasn't actually in the dumpster. This was just sitting on the floor there, as they often are. Doesn't seem to be any damage on it. I'm not seeing any physical damage. Anyway, I have actually powered it up and I get absolutely nothing. So it's highly unlikely to be a damaged panel, like a cracked panel or something like that, and failed electronics. That's pretty rare. So I suspect the panel's intact, but there's maybe, input fuse blowing, could be dodgy caps again. Who knows? So let's open this bad boy up and check it out, see if we can do a repair. And here's the back of it. It's really hard to manage one of these, like physically handle one of these things. Anyway, it is a bit how you doing in terms of like scratches and crap on the back. So I don't know where they came from. The legs are a little bit rusty on it. Discontinued, of course, but you can see it is pretty thin. Check that out. Bobby Dazzler. And the panel, for those playing along at home, technically it's a 49-inch. I think I looked up the data sheet, it's like 49.5 or, I don't know, like, 50-inch, 49, 50-inch. Ultra high definition, 4K. Not sure of the exact vintage of it. Anyway, it's got all the requisite stuff. We've got our USB 3s, we've got 2 HDMIs, we've got optical USB 2, we've got the Ethernets, a third HDMI. Don't know what this means though. Is that go ahead, will come pay for part Monday, 8th of the 7th? I don't know. Is it a repair jobby? Like I refurbed or something? First thing you want to do, of course, is check to see if it's actually drawing anything at all. I could hook my power meter up to it, but just measure the mains input there. It's completely open. Now, you'd expect something there, whether or not it's a switch. Of course, it's a switch mode, but it doesn't matter. Like if it's a switch mode or a linear, you expect to measure at least something. Not open. Yeah, that could indicate input fuse blown. All right, I think I got out most of the screws. Unfortunately, they aren't exactly the same. I think you can see a difference there in those. That's a little bit annoying. But this, I'm not sure if I have to take the legs off. Oh no, this one's on top. Damn it. Yeah, it looks like I have to get the panel for the legs off as well. And it's all very dusty and rusty, and I don't know where this thing's been used. All right, I think she's going to come off. Probably should lay this flat, but ta-da! We're in Lake Flynn. Look at it. You really need a decent sized bench if you're working on stuff like this. I should just clean the crap off here and get it done sideways. Anyway, power supply. And right off the bat, I spy with my little eye a PCB mount ceramic fuse there. So we'll measure that. And yep, of course, input fuse blowing. Why is it so? So this is where you start your visual inspection. You don't just go replace the fuse willy-nilly. This is interesting. Is this the Diode Bridge? Yeah, they've just got 4 regular axial diodes, one in 500 whatever, and they're just flapping around in the breeze there. They, of course, raise them up off the board like that for ventilation purposes and expansion of when they heat up, they can, the legs can expand and they don't crack and all the rest of it. Sometimes you might see them with like a little loop in them as well to take out any thermal stress. Okay, it looks like, is that a PTC? It's got an RT. Not looking for anything obviously blowing. The main DC input filter cap. Look at that. It's a sausage jobby. HBC. No, there's nothing blowing on the secondary side caps or anything. So magic smoke hasn't been released. Got input chokes, input caps, but no. The X and Y class caps down here, they look all intact. Everything looks fine, apart from the fuse being blown. So first thing I'm going to do, probably like measure, don't have to work out the circuit, just measure across the main DC cap here. Hello? Hello? That's a dead short on the output of the bridge rectifier here. Wow. Okay, we've got to fix that first before we, don't just go replace the fuse, because it just would have blown again. Okay, so there's no visuals on the top that I can see. I mean, we've got our switching tranny under there. Maybe we can get in a measure, but I've taken the screws off. Let's have a look on the bottom. Not seeing anything obvious. You might see a patch around there, but that looks like it's more, yeah, that's sort of like almost a conformal coat. It's hard to see this sort of thing on camera, but I can see it anyway. Hot and cold. I love how they call it hot and cold. There's cold on here. Where is it? There it is. It's cold. There's your optocoupler feedback. There's your hot side. I'm not seeing any blowing part or any magic smoke released. Not seeing it to give like a dead short. There's a dead short directly across there. There's no blowing traces. No, that looked like, no, that's all on the secondary side anyway. We're looking for a primary side short. Love the spark gaps in there. There you go. I've done a video on spark gaps and demonstrated them. That's really cool. It's always worth looking for any cracks on the input. That also could be a failure mode, like if the fuse measured right. Next thing I'd probably do is take the board out and just look for cracks on the mains input connector. But no, visually I'm not seeing it. We'll measure our diodes. Yep, they're all good. Yep, no wuckers. What's this bad boy down here? Oh, hello. We'll move that back to ohmsky range. And bingo, we might have found our culprit, because it's more likely that you get a dead short inside a semiconductor, like a diode like that. That is one of their failure modes. They can fail open and short than like inside the cap. Okay, I've pulled him out of circuit, and yep, that's the culprit. Measure across the mains cap again, and that's what we expect. We saw it charge up there. No wuckers. So there you go. We have a faulty diode. That is an MUR 460. There you go. It's an ultra-fast plastic rectifier, according to the data sheets. You could put probably any sort of equivalent in there to get it back up and running. So whether or not that's taking out anything else, so I don't know, maybe, can we take that's clipped, is it? Oh no, how is that held in? But yeah, maybe you could have a look under there, see if there's any blowholes in the driving tranny or not. But yeah, there doesn't seem to be any other damage. Usually you'd find something else. You can get other more obscure faults, like breakdown in the insulation of the enamel wire on transformers and stuff like that. But that's, that's pretty rare. So I just want to get in there and measure the transistor. It's not a bipolar jobby. It's one of those newfangled MOSFET-y things, because it's got G for a gate. Hey, drain and source shorted. There's another problem. Yep, it's not just the diode. So there you go. If you just tried to replace the diode there, and you'd probably come a gutser, and you might blow it again, because, well, our switching transistor's shorted as well. Damn. And out of curiosity, I just checked, you can actually buy complete replacement boards for this on eBay for $82. New old stock, or ripped from junked smash panel TVs and stuff like that. So, if you didn't want to like get the parts or whatever and try and debug this and spend the time on it, you can just spend, 80 odd bucks, at least here in Australia, and get a replacement board, and probably just work. It turns out this is a bit of a pain to get out. It's actually screwed in from the bottom side here, so you can't even release it from the top. And then it's soldered 3 solder tabs down in the board, so you've got to desolder 3 major tabs for the heatsink and the transistor itself, but it does lift out in one assembly. And that is an MDF 18N50. So that'd be, you can tell by the numbers on these MOSFETs, usually 18 will be the current, so that'll be 18 amps, so pretty beefy, and 50 won't be 50 volts, it'll actually be 500 volts. Because what I think's going on here is, you can see the architecture here. this is obviously our main switching transformer here, because here's your isolation, right? This is what this crosshatch indicates. This is your hot side, and this is your cold side, as they call it, or high voltage, low voltage. And so this is the isolation. It goes through, as I said, there's the optocoupler. So this is the main switching transformer here, and the main switching transistors for that, they've got to be on the bottom. So what this is over here, okay, you've got your mains coming in here, you've got your input filter, common mode filter section, you've got your bridge rectifier, and then you've got another switching element here, which is this transistor that we just took out here, and this little thing, which isn't a transformer, it looks like a choke. So when you see a switching tranny like this and a choke, and there'll be a chippy on the bottom, there's the controller there, and there's your choke over here. So that's interesting. That's actually 3 terminals there. But anyway, when you see that switching element after the bridge rectifier before the mains filter cap here, that's obviously doing active power factor correction. And if we were able to pull the part number off that, I'm sure we'll find the conformal coding makes it really hard to see a number on there, but I'll get it. So I'll bet you a Bitcoin that that's a power factor correction controller. Yep, I get to keep my Bitcoin. It's a 5590 power factor controller. And you can see up here that, as we said before, it basically is put between, this is your main big ass DC filter cap. So this is your AC input. There's your bridge rectifier. You'll have your, your common mode chokes and everything else. And this inductor is that big sort of transformer looking device we found, the 3 terminal jobby, and Q1. There's Q1 right there. That's our switching transistor, and there's our blown output diode. So both of these active devices here are blown. So what's caused that? Once again, I don't know. Like, one of them could have died and taken out the other or whatever. There could be an upstream fault up here or something like that. But, oh, geez, I don't know. Like, at this stage, you would just replace these 2 active devices, and because everything now measures fine across here. It doesn't, at least with the meter anyway. So, like, there's no dead short up here that's going to, blow this diode again and then maybe take out the transistor here. Who knows? So at this stage, I'd say, yeah, the best bet is to get a replacement diode, replacement transistor, and just power it up and cross your fingers. Although, that being said, you probably want to suspect the main DC filter cap as well. And I measured that in circuit, and it seemed to be okay. And there's no damage. Yes, I desoldered the thing because, yeah, I just thought it's worth taking the few seconds to get it out, and, we can just re-gunk it down there. They stick it down, stop it flapping around in the breeze, and, yeah, let's measure it externally. Let's put it in capacitatory mode, 87 mics. It's a nominal 100 mics, so, that's good enough. That's at 1 kilohertz. Let's just whack that up to 10. We expect that to drop a bit. Yeah, 79, still doing okay, and this probably won't measure at 100k, no, because it actually has, and at 100k, it actually changes ranges and has an issue. So we can't measure that, but that looks okay. And the DC resistance, the impedance, 0.4 ohms at 100 kilohertz. Yeah, that sounds good enough for Australia. Just for completeness, I will get an LCR meter that can actually measure the capacitance at 100 kilohertz, and that's at 1 kilohertz, 10 kilohertz, once again, 77 mic, 100 kilohertz, 17 mic, but that's to be expected. And if you don't believe me, we'll get a low ESR 100 mic cap. Bingo, 18.8 mic at 100 kilohertz. That's what it drops off at. And of course, that ESR again, we can actually measure series resistance. Yeah, 0.53. This one measures a bit higher at 100k, but yeah. So I deem that cap fine enough to go back in. I can't measure anything else. This diode here is fine. Everything on the secondary side seems to measure fine. All the caps look fine. Everything's hunky-dory. So we're going to replace the transistory and the diode. Now, by the way, if you didn't have these replacement parts, you could actually potentially just bypass this power factor correction system by simply removing the transistor and shorting out the diode there, or put in just a regular, replacement high voltage, suitable current diode in there, and then you simply got a regular full wave bridge here, which then goes into your main DC filter cap. Your power factor correction, all that does is, instead of basically presenting a capacitor across a bridge rectifier, and I've done videos showing how this is like a really poor power factor, they of course actively monitor it via the feedback here, and then switch the transistor and use this inductor to then deliver the power to the capacitor at the correct time, so that your mains over here doesn't think that this is a capacitor anymore. It thinks it's just a resistive load. You could leave the inductor there. It's not going to probably do a huge amount. You could just, to get it up and running again, just to prove that, or rather than spend all the time and effort. But anyway, I have done a complete video, which I will link in, and you've no doubt already seen it, which was a spoiler, where I went through ordering a suitable replacement part from RS Components here in Australia. It turned up. So we've got our transistor, we've got our diodes here. You had to buy them in a pack of 5, so no worries. And I completely forgot about the ceramic fuse, which has blown, of course. This is a 5 amp HRC one. I don't have one of these suitable, especially a leaded one like this. But I do have in stock some 5 amp axial ones like this, which should work a treat. These are 250 volt rated. These axial ones typically come in, either like low voltage ones designed for like secondary side DC fusing and stuff like that. You don't want to use those on primary side mains, but these are proper 250 volt rated. They're not as beefy as this big ceramic one, but these are actually ceramic inside, believe it or not. So yep, that'll be good enough for Australia. So let's whack the transistor and the diode in and put the cap back and power it back up. Solder out of these holes. They're annoying. No whackers. Let's probe up the clacker. 450k, there you go. So you'll notice something's missing in there. The transistor and the heatsink. I've deliberately left that out so that we actually have the circuit like this. I've removed the transistor. I put the diode in because you can either short out the diode or leave it in. It really makes no difference. And we'll see if it powers up without the power factor correction circuit, because without the transistor in there to do anything, with the inductor to short it out, then it's just basically, it's going to be DC through the inductor, through the diode, into the cap like that. It's not going to be the most efficient thing, and of course it'll have zero power factor correction, but who cares? Let's just see if that works. Well, as I said, that will get it actually up and running, and it'll probably just work fine forever without the power factor correction if you're happy with the extra load, which you're typically in your residential applications, and I've done videos on this, in your residential household, you're not going to pay for poor power factor devices, although, it's not good for the environment, of course. You want to put the transistor in if you can, but still, you're not going to pay for it. Well, okay, Dave, technically you are going to pay for it in terms of like increased utility costs, because you pay a fixed fee and that pays for all the infrastructure. If everyone had removed their power factor correction transistors like this from their TVs, then the utility company would have to install greater transmission line capacity, bigger lines and everything else, more power generation. It's got to come from somewhere, it's not magic. And I know you're curious to see how much this actually draws before and after the transistor. So this is with no power factor correction. This is in standby. It's drawing 327 milliwatts. Power factor of 0.02. Yeah, it's pretty bad. So if we check out our VA, it's actually drawing 17.5 VA, or I don't want to say 17.5 watts because it's VA, but you'll only actually pay for 0.3 watts. You won't pay for 17.5 watts, you'll only pay for 0.3, so very poor power factor. Let's switch it on. And 16 watts, 98 watts, yeah, 100 watts, that's what I expected. Our power factor, there you go, it's gone up to 0.5 as you'd expect. It improves. It's very poor at low power factors. So, 0.5, that's not too shabby. So, that's 194 VA, but, you'd only be paying for that 99 watts still. Let's power that on. Oh, it's flapping around in the breeze. She'll be right. Yay! Winner, winner! Chicken dinner! I see Hitachi on the screen. As I said, you really do need like a really lot of bench space to work on these large screen TVs. There we go, got red down the bottom. That was the standby, was it? Hitachi, inspire the next. The next what? Inspire the next repair. It is, remember, this is a 4K, none of that regular HD rubbish. Geez, that took some time, didn't it? It's got the Netflixes, it's got the YouTubes, it's got the Twitteries. I was shadow banned on Twitter, by the way, if you weren't aware. Shadow banned for like a week. It eventually just magically disappeared. I don't know, it could be shadow banned again, who knows. Got all white on the screen. It's looking really good. It looks all washed out on camera, but trust me, it's good. Oh no, it's going to have to go straight back to the dumpster. This is how it turned up in the dumpster. Aliens. It's always aliens. Actually, it turns out once you get to this 404 error here, the soft buttons on the back do absolutely nothing. I can't even power it off. See if we can do a network firmware upgrade, shall we? It does connect to the networks. By network is log in. I'm sure, right. There's a t-shirt in that. There's a Hitachi t-shirt with is log in. Cannot connect the Huon web. Please check your status. This is hilarious. And it's not formatted properly, but there you go. There's a Raspberry Pi HDMI input. No wuckers. Works a treat. All right, so it works fine without the power factor correction, but now I've added back in the new transistor, and let's give it a whirl. Hopefully we don't release the magic smoke. And 3.2 watts. There you go. So it actually draws more in standby with the power factor correction. Oh, that's a shocker. That's terrible. And the power factor correction's not that great. It's better, but 0.16. But this is typical of low power products like this. That's not great at all, is it? Anyway, let's switch it on. Wow, well that's very interesting. It doesn't work at all with the switching transistor. Are you kidding me? Well, that actually makes no sense at all, because if the switching transistor just wasn't, let's say the switching IC, let's say that was busted and it just wasn't driving that transistor at all, the transistor would just sit there open and it shouldn't do anything. It'd be just like it's removed. But in any case, it's drawing like a couple of watts, so something's going on, but there seems to be now no standby power presumably going to the logic board. What the? I don't get it. Just a shout out to small design touches like this. The standoffs that they've actually used, which are, it looks like they're embedded into the frame down here, they have little extender notches on them where it fits into the board like that. So the board, even though it's vertical, can stand there. Brilliant. Someone was thinking. Didn't really want to have to probe around on this thing. I thought I was going to have a winner chicken dinner and get this thing fixed. But anyway, let's have a probe. You've got to use your high voltage probe here. Got the HVP 70. And by the way, this design, I've got it unplugged right now, but the cap is still charged up because they didn't design in a bleed resistor. And you'll notice over here, that's 50 volts per division, 50, 100, 100, and it's still charged up to 150 volts DC. It's slowly going down due to the load of the probe, which is 4 meg, so it'll eventually bleed off, but they've got no bleed resistor on there at all. So just be careful. If you're going to do that, use your meter in low Z mode, if your meter has that, for example, and then like short out the main filter cap on these things when you take it off. Anyway, let's power this thing up and see what we get. There we go, of course, yep, 340 odd volts, something like that. That's what it expects. So our DC is there, but for some reason, our soft control isn't switching it on like it did before, which is very unusual because the power factor correction circuit, that transistor and that 5590 IC, isn't it? That's basically a completely independent circuit. As you saw, it worked fine without it. It's not tied into the switching standby or anything like that. There's nothing. This is on the primary side, mains primary side. There's only those two optocouplers over here. These two optocouplers coming back, and that's it. So there's nothing coming back onto that primary side. So I'm at a loss as to how that is not powering up like it did before. Maybe it's somehow the switching of this is tied into the switching controller of like the main switching controller over here, perhaps, which is not giving any voltage on the secondary. It's got to be it. There's got to be no voltage on the secondary. If there was, it should just work like it did before. Very puzzling. You can see that cap slowly discharge. That's 10 seconds per division. It'll take a long time to discharge at 4 meg. Okay, just a quick check of the voltage on the secondary. Don't want to take any chances. Don't want to accidentally brush anything on the primary side. So we've got our takeaway container protection here. And let's measure. Okay, powered on. Now, this is the V power going over to the board. So luckily, they've got the pinouts on here. Yep, nothing. So yeah, I didn't expect that to come on unless the standby was on. The one next to it, that should be V standby. Don't short it, Dave. Don't short it. No, we're getting nothing on V standby, which is why it is not powering up. We'll just discharge that cap again. There we go. Boom. Drops it down to 8 volts. Yeah, no wuckers. So that's very curious. Why, if we're getting our full voltage on our main filter cap, that should be powering the switching circuitry, which is under here, which drives the transformer primary, which then should switch that, and we should get voltage on the secondary. And then of course this has the standby signal comes back on this connector and then tells this board to provide full power out, but there's no standby voltage there. Unless I'm measuring it wrong. I don't have a schematic for this thing. If you do, leave it in the comments down below. So all I can think of is that, as I said, this switching controller for the power factor correction is somehow tied into the main switching controller over here, which makes no sense because this is supposed to be a completely independent circuit. It's not tied in at all, yet it works without the transistor. It just passes the standard bridge rectifier, passes through the diode into the main filter cap, and everything's hunky-dory. Everything powers on just fine. So that is really puzzling. Now, unfortunately, this video's gone on long enough, and in show business, they always tell you, leave people wanting more. So I'm not going to go any further with this in this video. Maybe that's for another video, and people can speculate what's actually going on here. So I'm just going to remove that transistor again, get the TV going, and we might have to revisit this one because that's very interesting. Leave your thoughts in the comments down below. And here you go. I have actually lifted the pins on this, so I'm going to power this up again. So transistor is now missing. Didn't have to get the whole heatsink out. Well, what do you know, damn it? Look at this. 3 watts. Again. I betcha it's not going to soft power up. Something has gone wrong with it since after I've installed that transistor, and then I've removed it again, and it's... Alright, I've physically removed the heatsink again, so it's exactly the same thing. I haven't done anything to it except put that transistor in, power it up, and take the transistor back out. And you saw it was working before, and now it's... Nope, we've still got the 3 watts. So this is some sort of new fault. Unbelievable. Yep, confirmed. I just tried the standby button, and sure enough, it doesn't work. So, by reinstalling the transistor, have I damaged something else? Wow. Okay, this was a repair. and then I killed it by repairing it more, I guess. Catch you next time.